On September 15th, 2017, a spacecraft the size of a school bus traveling at more than 100,000 kilometers an hour sent its final transmission to Earth from inside the atmosphere of Saturn. 91 seconds of data, and then nothing. It would take scientists years to fully process what was buried in that final transmission, and in the months of measurements that preceded it. Not a message. Not anything built by another intelligence. Something stranger than either of those, because it was real. It was measured by working instruments, and it directly contradicted models that planetary scientists had spent decades building. The region between Saturn and its rings, a gap no spacecraft had ever entered, one engineers, genuinely worried might tear the probe apart, turned out to be almost empty, in a way nobody could fully explain. A magnetic field that, according to the physics used to describe every other planet, should not exist in the form it does. And on a small moon that Cassini kept returning to for over a decade. A final missing ingredient for the chemistry of life, discovered not during the mission itself, but 6 years after the spacecraft was gone, buried in data nobody had the tools to fully read at the time. This is the real story of what Cassini found in its final months. Documented, peer-reviewed, still actively being argued about by planetary scientists today. No aliens, no cover-ups, no hidden signals, just a spacecraft that worked exactly as designed, returning data that the best physics available still cannot fully explain. To understand why those final measurements mattered so much, it helps to know what scientists thought they already understood going in. Cassini arrived at Saturn in July 2004 after a 7-year journey from Earth. Over the following 13 years, it completed nearly 300 orbits, flew past Saturn's largest moon titan well over 100 times, made more than 20 close passes of the icy moon Enceladus, and sent home hundreds of thousands of images, along with an enormous volume of scientific data. By any measure, it was one of the most productive planetary missions ever flown. By 2017, when mission planners made the decision to end it deliberately, plunging the spacecraft into Saturn's atmosphere so it could never accidentally contaminate one of Saturn's potentially life-bearing moons, scientists felt they had a reasonably complete picture of the system. They knew about the 6-sided storm parked at Saturn's North Pole, a persistent hexagonal jet stream first photographed by Voyager back in 1980, and still there, still rotating, when Cassini showed up 24 years later. They knew the ring system in intricate detail. The named bands, the gaps carved out by gravitational interactions with nearby moons, the wave patterns rippling through the ring material like something moving across the surface of a pond. And by 2005, they knew about water erupting from cracks near the south pole of Enceladus, a discovery that reshaped where in the solar system scientists thought conditions for life might exist. What nobody knew was what sat in the narrow gap between Saturn's innermost ring and the top of its atmosphere, a region roughly 2,000 kilometers wide, which sounded enormous until you set it against the scale of Saturn itself. That gap had never been sampled directly. The assumption going in was that it would be full of small ring particles, dangerous to a spacecraft moving through it at orbital speed, and for 13 years, mission designers had kept Cassini well clear of it. In the mission's final phase, called the grand finale, controllers took the calculated risk of sending Cassini through that gap 22 times between April and September 2017, and what its instruments found there was not what anyone had modeled. Before those orbits began, mission scientists ran predictions of what the gap probably held, a region moderately dense with small particles, dust shed from the inner rings, charged grains that would need careful navigation to protect Cassini's instruments. For the very first pass, the spacecraft was oriented with its large dish-shaped antenna facing forward, using it as a shield against expected particle impacts. When the data came back, the particle count was dramatically lower than predicted. Not slightly lower, dramatically lower. Cassini's radio and plasma wave instrument, which converts particle impacts into an audible signal, was expected to register a steady stream of pops and cracks as it crossed the gap. Instead, the recording came through almost clean, closer to the ordinary whistles and squeaks of the surrounding charged particle environment than to anything resembling a debris field. Cassini's own project manager at the time, Earl Maze, described this region simply as the Big Empty, and admitted plainly that the team did not know why it was so much cleaner than the models said it should be. That single result changed the rest of the mission in 2 ways. Practically, it meant the gap could be used more freely than the original plan allowed, which is part of why Cassini ultimately made all 22 passes rather than a more conservative number. Scientifically, it meant that something was actively keeping the gap clear against the constant inward drift of ring material, and that something has never been fully identified. Electromagnetic effects tied to Saturn's magnetic fields sweeping charged particles out of the region is one candidate explanation. It remains an open question, not a solved one. The second surprise from that same gap is stranger, and it's the one that shows up in peer-reviewed papers using phrases like difficult to reconcile with any known process. As Cassini made its passes, its I.O. N and neutral mass spectrometer, an instrument built to identify the chemical makeup of whatever gas or particles it encountered, sampled the thin material drifting between the rings and Saturn's upper atmosphere, and it found things that did not belong there. Not simple hydrocarbons like methane, but larger, more structurally complex organic compounds, with molecular masses suggesting formation processes that don't operate easily in that environment. Building organics of that complexity generally requires a specific combination of temperature, pressure, available precursor molecules, and enough time for those molecules to react and assemble. The ring atmosphere gap offers almost none of that. It's extremely cold, it's close to a vacuum, and Saturn's magnetic field bathes the region in radiation intense enough to tear complex molecules apart rather than build them. Finding sophisticated organic chemistry there was, as some scientists on the mission put it, like finding an intact piece of machinery sitting in the middle of a desert with no roads leading to it. The object is undeniably there. How it got there, or how it assembled in place, is not obvious. Hunter Waite, the instrument's principal investigator at the Southwest Research Institute, described the incoming material bluntly. Not the simple water ice everyone had assumed, but a genuine chemical cocktail. Water, yes, but also organics, fine silica particles, and other compounds suggesting the rings themselves are far more chemically active than anyone had modeled. One proposed explanation is photochemistry, sunlight slowly building more complex molecules out of simpler ones over long stretches of time. But the complexity Cassini actually measured outran what those photochemical models could produce. That gap between prediction and measurement is real, it's published, and as of now, it isn't fully resolved. There was also silica in the mix. Fine silicon particles, similar to material found in ordinary sand and rock, ground down presumably by impacts within the ring system itself. Their presence pointed to erosion happening somewhere in the rings, but the amount and distribution Cassini measured didn't line up cleanly with existing erosion models either. A wall of this material, ice, organics, silica, falls continuously from the rings into Saturn's upper atmosphere in a process scientists call ring rain, a term that existed well before Cassini measured it directly, based only on indirect evidence. What the grand finale orbits confirmed is that ring rain is heavier, chemically richer, and more variable by latitude than any earlier model had captured. The third surprise came from Saturn's magnetic field, and this one reaches into questions about how planets generate magnetism at all. Every planet in the solar system with a significant magnetic field, Earth, Jupiter, Saturn, Uranus, Neptune, generates it the same basic way, through the motion of electrically conducting fluid deep in its interior. On Earth, that's the molten outer core, mostly liquid iron, churning under the combined influence of internal heat and the planet's rotation. On the gas giants, it's hydrogen, compressed under such enormous pressure that it behaves like a liquid metal, conducting electricity as it moves. A basic feature of any magnetic field generated this way is that its axis, the line running through the magnetic north and south poles, should sit at a measurable tilt relative to the planet's actual rotation axis. Earth's magnetic poles are offset from its geographic poles by roughly 11 degrees. Jupiter's tilt is close to 10 degrees. Uranus and Neptune are far more extreme, with tilts over 50 degrees. Saturn breaks this pattern entirely. Even before Cassini's final orbits, its magnetic field was known to be aligned with its rotation axis to within about a degree, which was already strange enough to generate its own body of theoretical work. The grand finale measurements, taken as Cassini repeatedly, dove through the strongest part of the field, produced the most precise reading of that alignment ever made. The result? A tilt of less than 0.0095 degrees, under a hundredth of a degree. Michelle Doherty, the magnetometer's principal investigator at Imperial College London, put it about as directly as a scientist can in a published paper. This level of alignment poses a fundamental challenge to existing models of how planetary magnetic fields are generated at all. There's a mathematical result in the standard theory, known as Cowling's theorem, which holds that a magnetic field generated by fluid motion cannot remain perfectly symmetric. Something has to break that symmetry, tilting the field at least slightly away from the rotation axis. Saturn's field is not perfectly symmetric. There's some genuine uncertainty in the measurement, and there are almost certainly small asymmetries current instruments simply can't resolve. But it is close enough to perfect that explaining it requires mechanisms with no confirmed precedent anywhere else in planetary science. A stably stratified layer deep in the interior that damps out any tilt through helical convection is one proposal. Differential rotation between layers, smoothing the asymmetry away, is another. Neither is confirmed. As of now, why Saturn's field is aligned this precisely remains one of the genuinely open problems in planetary science. None of that was anticipated going in. All of it came from clean, well-calibrated instruments functioning exactly as designed, right up until the spacecraft entered Saturn's atmosphere for good. But arguably, the single most extraordinary result connected to Cassini didn't come from those final orbits at all. It came from a different world entirely, and from a discovery made 6 years after the spacecraft was already gone. Enceladus, Saturn's sixth largest moon, is roughly 500 kilometers across and covered almost entirely in fresh, bright ice, making it one of the most reflective bodies anywhere in the solar system. In 2005, Cassini discovered that Enceladus has an active geological process running continuously at its south pole, a set of parallel fractures nicknamed the Tiger Stripes, from which plumes of water vapor and ice are erupting into space, material that goes on to form Saturn's faint outer E-ring. The discovery was immediately significant because sustaining an active process like that on a body as small as Enceladus requires an internal heat source. And Enceladus is far too small and too distant from the sun to be warmed meaningfully by sunlight. The heat instead comes from tidal flexing, the gravitational tug-of-war between Enceladus, Saturn, and neighboring moons like Dione, which squeezes and stretches the moon's interior rhythmically enough to generate real friction and real heat. That heat is enough to sustain a liquid water ocean beneath the ice shell, with the Tiger Stripes acting as the connection between that buried ocean and open space. A liquid water ocean, in other words, sitting far outside the solar system's traditional habitable zone. That single fact reshaped how scientists think about where life might be possible. Over the following years, Cassini made repeated passes through those plumes, building up an increasingly detailed chemical picture. The plumes contained water ice, as expected. They contained simple organic compounds. And critically, they contained molecular hydrogen, a detail that mattered enormously because hydrogen in the plume is a strong signal that hydrothermal reactions are happening on the ocean floor, hot water reacting with rock in a process called serpentinization. On Earth, seafloor hydrothermal vents support entire ecosystems that don't depend on sunlight at all. Finding evidence of the same kind of chemistry at Enceladus was one of the most significant astrobiology results to come out of the entire Cassini mission. By the time the mission ended in 2017, the chemical inventory pulled from Enceladus's plumes included water, molecular hydrogen, carbon dioxide, methane, and a range of other organic compounds. 5 of the 6 elements considered essential to life as we understand it: carbon, hydrogen, nitrogen, oxygen, and sulfur. The 6th, phosphorus, was missing from the confirmed list. That's not a minor gap. Phosphorus is a structural backbone of DNA and RNA, the molecules every known living thing uses to store genetic information. And it's central to ATP, the molecule cells use to store and move energy. Without it, life as we understand the term doesn't work. Cassini's instruments during the active mission simply weren't sensitive enough to detect phosphorus compounds at the concentrations actually present, so the question sat unanswered when the spacecraft burned up in 2017. In June 2023, nearly 6 years later, the answer came from a different direction entirely. Frank Postberg, a planetary scientist at the Free University of Berlin, who had spent years working with Cassini's archived data, led a team that went back through measurements from Cassini's cosmic dust analyzer, an instrument that had sampled countless ice grains from Saturn's E-ring, the ring built from Enceladus's own plume material. Using improved analysis techniques that didn't exist during the active mission, the team found clear evidence of sodium phosphates in those ice grains. Not trace amounts, but concentrations of phosphate, at least 100 times higher than what's found in Earth's oceans, and by some estimates possibly closer to 1,000 times higher. Phosphorus, in Enceladus's ocean, in abundance, sitting in water that was already known to be alkaline, chemically active, and hydrothermally heated. The paper appeared in Nature in June 2023, and its authors were direct about what it meant. Enceladus was now the only place beyond Earth with confirmed evidence for all 6 of the elements considered essential to life as we know it: phosphorus and sulfur, sometimes shortened to the acronym CNOPS. The James Webb Space Telescope has since added its own confirmation from a different angle, capturing images showing that the plume's water vapor extends into a vapor cloud spanning the entire E-ring, far larger than anything Cassini had been able to fully map during its own flybys. Cassini found the ocean. Cassini found the heat. Cassini found 5 of the 6 essential elements while it was still operating. And scientists went back into Cassini's own archived data and found the 6th, years after the spacecraft was gone. None of this confirms life exists at Enceladus. There is no observation from Cassini or anyone since that shows biological activity actually occurring there. Having every necessary ingredient present doesn't guarantee anything has assembled into something living. But the distance between we don't know if the ingredients are even present and we don't know whether the chemistry has gone on to become biology is the entire scientific journey that ran from the discovery of Enceladus's plumes in 2005 to Postberg's phosphorus paper in 2023. Cassini itself never detected life. What it did was more durable than a single life detection claim could ever be. It systematically built the case, piece by piece over 18 years, that a small icy moon nobody had reason to look at closely before 2005 has every physical and chemical condition that life, as science currently understands it, requires. It's worth pulling the focus back to Saturn itself for a moment, because the deeper Cassini story isn't only about Enceladus or the strange chemistry in the ring gap. It's also about how much remained genuinely unknown about a planet humans have been watching with the naked eye since before the invention of the telescope, and that a dedicated spacecraft studied up close for 13 straight years. Saturn radiates noticeably more energy than it receives from the Sun, a trait it shares with Jupiter, though the underlying mechanism isn't fully settled for either planet. On Jupiter, the excess is generally attributed to primordial heat left over from formation, slowly released as the planet contracts under its own gravity. That explanation works less well for Saturn, which is smaller and, by the models, should have radiated its formation heat away much, faster than it apparently has. One leading alternative involves helium slowly separating from hydrogen deep in Saturn's interior and raining downward through the surrounding hydrogen layer, releasing gravitational energy as heat along the way. But the existing models of that process don't reproduce the actual measured excess heat with the precision the data demands. Saturn's atmospheric behavior, tracked by Cassini in far greater detail than any previous mission managed, kept producing its own surprises throughout the 13 years. The hexagonal polar storm turned out to contain nested jet streams, internal wave structures, and embedded vortices interacting in ways that atmospheric models still struggle to fully reproduce, and exactly what sustains a stable hexagonal shape in a planetary atmosphere. VOS, rather than the more typical circular or oval storm systems, remains an active research question. A massive storm that erupted in Saturn's northern hemisphere in 2010 and 2011, the largest and most intense observed on any planet since the Voyager era, eventually wrapped entirely around the Io planet, and as Cassini tracked its evolution, it detected chemical signatures, including unusual water and phosphine signals, produced by the storm dredging material up from deep in the atmosphere to much higher altitudes than expected. Phosphine's presence on Saturn has actually been known for a long time, and it's remained a standing puzzle because ultraviolet radiation in the upper atmosphere should destroy the molecule faster than any known process can ignore resupply it, meaning either the resupply is more efficient than current models allow, or the destruction happens more slowly than calculated, or there's some production mechanism at work that hasn't been identified yet. None of that is resolved. All of it is still being actively worked on, using Cassini's own archived data alongside newer observations from missions and telescopes that came after it. The documented peer-reviewed story of Cassini's final months contains no alien transmissions, no hidden encrypted messages, no cover-up. What it actually contains is, in the true scientific sense, more remarkable than any of that. Proof that a planet studied for 4 centuries still holds fundamental properties nobody fully understands, discovery of a moon whose ocean now satisfies every known chemical requirement for life, measurements of a ring system more chemically active and dynamically complex than any model predicted, and a magnetic field so precisely aligned that it challenges the basic theoretical framework used to explain how every other planet in the solar system generates its own field. These aren't comfortable results. They aren't the kind of findings that let planetary scientists close the book and move on. They expand the list of open questions rather than shrinking it. They leave Saturn more mysterious today than it was before Cassini arrived, not less. After 13 years of continuous observation by the most capable spacecraft ever sent to the outer solar system, Cassini's signal disappeared on the morning of September 15, 2017, as the spacecraft broke apart entering Saturn's atmosphere at more than 100,000 kilometers an hour. At the Jet Propulsion Laboratory, the science team watched the signal strength hold steady until atmospheric drag finally overwhelmed the spacecraft's ability to keep its antenna pointed at Earth. And then it simply stopped. People who had spent the better part of their careers on that mission were visibly emotional watching it happen. 13 years of relationship with a distant planetary system ended in 91 final seconds of transmitted data before the spacecraft that carried the instruments was gone entirely. But the data it had already sent home didn't stop being useful the moment the signal ended. The phosphorus discovery came in 2023. New papers on ring chemistry are still being published. The magnetic field alignment remains one of the most actively studied subjects in astrobiology, and the James Webb Space Telescope, which only began operating in 2022, has since added its own observations of the Saturn system that extend and confirm parts of what Cassini measured years earlier, including that far larger water vapor cloud around Enceladus that Cassini itself never fully mapped. When Postberg's team found phosphorus buried in a spacecraft's decade-old archive, they were using instruments and analysis methods that didn't exist while Cassini was still flying. That's one of the most important and least discussed truths about planetary missions. The raw numbers sit in an archive indefinitely, and as the tools available to interpret them keep improving, that archive keeps yielding findings. The original instruments were quietly recording all along, long before anyone had the means to actually see them. There is almost certainly more still sitting in Cassini's data. The open question now isn't whether the archive has more to give up. It's which questions still need to be asked and which new tools need to be built to find it. The most advanced proposal currently on the table is a dedicated return mission to Enceladus, one built specifically to fly through the plumes, carrying instruments an order of magnitude more sensitive than anything Cassini carried. Sensitive enough to search directly for amino acids, lipids, and other complex biological molecules, rather than only the chemical conditions that would make their presence possible. That mission hasn't been selected or funded as of 2026, but the case for it rests entirely on what Cassini already found. The ocean is there, the heat is there, the full chemical inventory required for life is there. The only question the instruments sent so far have not been able to answer is whether anything is actually alive in it. That's the question a future mission would exist to answer, and the foundation for it was laid by a spacecraft that burned up over Saturn on a September morning, transmitting its last readings for 91 seconds as it went, closing out a 13-year conversation between human science and the second largest planet in the solar system. The conversation is over, the questions it left behind are not, and scientists are still, right now, working through what it actually told us.